Hi everyone. In this lesson, we will look at section 3.3, rational functions in the form of f of x equals ax plus b over cx plus d in the grade 12 advanced functions course. Warm up. How would you graph y equals to 3 over x plus 3 plus 2? You should note that this is a transformation of the reciprocal function, the one that looks like a butterfly. So the x plus 3 in the denominator suggests that we are shifting the function 3 units to the left. The plus 2 at the end shows that we are going to translate 2 units up. And then the 3 at the top here is really the a value, which tells us that we should be vertically stretching the original parent function by a vertical factor of 3. What you also notice is that, well, with the reciprocal function, it has a horizontal and a vertical asymptote. So where are they located now? With the translations, your vertical asymptote will be at x equals to negative 3, and your horizontal asymptote will be at y equals to 2. And then this is not reflected, so we know that the branch on the right sits at the top right side, and then the branch on the left sits at the bottom left side of the two asymptotes. Unfortunately, my program doesn't allow me to plot dotted lines, so they appear as these green lines here when I'm graphing these asymptotes. If you're doing it by hand, I suggest that you draw them using dotted lines. So let's take this one step further. How can we write, or is it possible to write y equals to 3 over x plus 3 plus 2 in the form of y equals to ax plus b over cx plus d? Well, the answer is yes, because the plus 2 at the end of the original function has a denominator of 1. So if I try to give it the same denominator as the first term here, x plus 3, I will be multiplied 2 by x plus 3 over x plus 3, which allows me to simplify the numerator and rewrite my function as y equals to 2x plus 9 over x plus 3. So we say that these two functions, even though the form of the algebraic expression looks different, they are actually equivalent, which also means that they will share the exact same characteristics. They will have the same vertical asymptote, the same horizontal asymptote, one each, and also they will have the same x and y intercepts, and these points will help us to make the graph, and also the graph of both functions will have two branches. So we're going to examine this rational function, or like a quotient of two linear functions, further in the examples below. So we start with the function f of x equals to 3x plus 2 over 4x minus 1. For this type of function, you will always need these four features: x-intercept, y-intercept, vertical asymptote, and horizontal asymptote. So we start with the x-intercept. So x-intercept is finding the x values where the function is equal to 0, because that's your x-axis crossing. So equate 0 to 3x plus 2 over 4x minus 1. You can simplify and find that x is equal to negative 2 over 3. For y-intercepts, you set x to 0, you evaluate f of 0, and then that gives you a y-intercept of negative 2. So those are the easier features. Now moving on to the vertical asymptotes. So if you recall from last year in grade 11, when you are simplifying rational expressions, you always had to state restrictions by looking at the denominators. So basically, the denominators will tell you where your function is undefined, because you can never divide by 0. So the position of your vertical asymptotes, in other words, would be found, or you can find that by setting your 4x minus 1 in the denominator equals 0 and solve for x, which gives you x equals to 1 over 4. There's a little more to finding or learning more about the function around the vertical asymptotes. We can also study the behavior of the function near x equals 1/4 or 0.25. We want to know whether the function is approaching this value, this position on your graph from positive or negative infinity. So we can do that by using what we call test points. For instance, if I want to know the behavior of the function as x approaches 1/4 from the left, which is this negative sign here, I'm going to pick a number slightly smaller than 0.25. So let's say you pick 0.24999. You substitute that into your function. You should notice that it gives you a negative number that is quite negative, so very large or very small, depending on how you look at it, but far from zero for sure. So we can conclude that as x approaches 1/4 from the left, the function f of x approaches negative infinity, because the test point tells us so. So you can do the same thing to see as x approaches 1/4 from the right. So this time pick an x value that is just slightly bigger than 0.25. So let's say 0.25001. Your function should turn out to be a positive number. So we say that the function approaches positive infinity. Moving on. For horizontal asymptotes. Horizontal asymptotes really tells us the behavior of the function as x becomes or approaches infinity. When I don't write the positive or negative sign in front of infinity, I mean infinity in general, so on both ends. There is a formal way to come up with the equation of horizontal asymptotes called the limit. I'm going to show you once here. It will be very useful in calculus. But for the sake of this course, if you don't want to use the limit notation, you can use the shortcut. But let's take a look at the limit first. So formally we say that, well, as x approaches infinity, where will the function 3x plus 2 over 4x minus 1 approach? So you write it out like this. To evaluate this limit, the rule of thumb is to divide every single term by the highest power of x found in your original function. So I have 3x and 4x, which means that we need to divide all the terms by x. So you write it out like that. You simplify it, and now it looks like we're looking for the limit as x approaches infinity of 3 plus 2 over x over 4 minus 1 over x. What does this mean? This means if x is a really large number, let's say 1 million, okay? What will the value of this whole unit become, or gets really close to? So imagine if I divide 2 by 1 million, what number will it get really close to? It will be almost 0. Now here, if I divide 1 by 1 million, it will also turn out to be a number that is very close to 0. So what is 3 plus very close to 0? About 3. What's 4 take away very close to 0? About 4. Therefore, we say that the limit of this thing as x approaches infinity is 3 over 4. Okay, which means that the horizontal asymptote of our function is y equals to 3 over 4. Using the shortcut, you notice that the 3 and the 4 actually matches with the 3x and the 4x that you see in this form of a function. So in this course, we can say that the horizontal asymptote is always y equals to a over c. So as x approaches negative infinity, well, you can use test point again, plug in, let's say, negative 1000 into f of x. You should notice that the number will be smaller than 3 over 4. So the function approaches the horizontal asymptote from below as x approaches negative infinity. And as x approaches positive infinity, so use a test point of f of 1000, let's say, you will notice that the value that you get will be higher than 3/4, which means that the function f of x will approach the horizontal asymptote on the far right from the top, or from above the horizontal asymptote. So when you put these all four of these features together to make your graph, so here are your intercepts, these 2 points here. You have your horizontal and vertical asymptotes, and then the behavior of your function from the right side of your VA is positive infinity, and from the right side, on the right side for your HA, it's above the horizontal asymptote, gives you this branch, and then the other branch looks like that, okay, following similar logic. So this is example 1. Move on to part 2 of this video to continue with the lesson.